Interested to find how many photons with wavelength between 500 and 501 nanometer coming out from this small hole when this black body is at 7500 Kelvin. Okay. So what we're going to do here is first let us calculate what is the power coming out from this hole for photon with that wavelength. I shall call 500 as lambda 1, 501 as lambda 2. So I'm interested in the wavelength coming out from lambda 1 to lambda 2. But also bear in mind, lambda 1 and lambda 2 is very close. It's actually a very narrow band, right? So let me first find out what is the power coming out. Let's assume that there are n photons coming out per second over this band of wavelength, n of them per second. So the power that you can detect will be the number of photons coming out multiplied by the energy of each photon, which I call E. Agree? So how many photons coming out per second multiplied by the energy of each photon will give you the energy coming out per second, which is the power. Agree? And the energy of the photon can be written as hf or hg over lambda. Now over here, we are not talking about one wavelength, but we're talking about a band of wavelength. However, we know that this band is very, very small. So as an approximation, we shall take the wavelength as an average of 500 and 501. So lambda 1 plus lambda 2 over 2 is used to represent the average wavelength. Otherwise, I have to really consider from 500 to 501 all the different wavelengths. But for simplicity, I shall take the average of the two and use it to represent the wavelength of that band of photon coming out. So therefore, the lambda is now approximated as an approximation of lambda 1 plus lambda 2 over 2. Now this number is essentially 500.5. Agree? 500 and 501, the average is 500.5, midway in between. So after that, I rearrange, I get the power coming out. So far, so good. Now this is a macroscopic picture. I'm counting how many photons coming out over that wavelength, and from there I try to obtain an expression for the power. Okay, next. Now another thing about Planck's radiation law is that the power emitted over any wavelength is the area under the curve. You all learn about that, right? For the Planck's radiation law, if you want to find what is the power emitted over a band of wavelength, you just find what is the area under the curve over that band. That gives you the power. So let's say this is the Planck's radiation law at 7500 K. I'm interested in finding what is the power emitted from 500 to 501, lambda 1 to lambda 2. What I need to do is just to find the area under the curve, this shaded area. That shaded area will be this quantity, right? And that is from the theoretical aspect. This is the theoretical aspect. This area will give me this power emitted. Is it okay? Now, I want to highlight something here. You know, for this spectral intensity that we plot, which is essentially the Planck's radiation law, what is the unit of R? Have you ever paid attention to the unit of R? It's very important because we are dealing with physics, science. Everything has unit, right? And carries some physical meaning. The unit of R is watt per meter cube. And R is not a physically meaningful quantity. The physically meaningful quantity that can be measured is the area under the curve, which is the power. The area and the curve represent the power. Now, what is the unit of an area like this? Area is height times base, right? So the unit will be unit of R times the unit of the wavelength. So watt per meter cube multiplied by meter becomes watt per meter square. That's why this area represents power. Watt per meter square, right? Power per unit area. Okay, so what we want to do here is to find what is the area under the curve. So I write it like this. You pay attention to here. The integral of Planck's radiation law from wavelength 1 to wavelength 2, what does it represent? It represents power emitted per unit area, watt per meter square. You see, I highlighted the unit. So this integral, which is the area of the curve, has a unit of watt per meter square. Okay? So it tells us what is the power coming out per unit area. But remember that here we are observing over a certain opening. So I take that power per unit area, multiply by the area of that opening, which is pi r squared, or pi diameter over 2 squared. Then that product will give me the power coming out. Are you all clear about this expression? This is the area under the curve from 500 to 501. It has a unit of watt per meter square. And I take this, multiply by the physical area, pi r squared. It will give me what is the power emitted in watts. See, this has a unit of meter square. This has a unit of meter per watt per meter square. So meter square cancel out, you get watts. So this whole thing gives me the power coming out. So far so good, everybody? Okay, so we look at the power coming out from lambda 1 to lambda 2 from two perspectives. One is in terms of how many photons coming out and calculating the energy of each photon. And the other one is to base on Planck's radiation law that give me what is the power emitted from a black body over a certain band. So in fact, this P should be equated to this P to solve the problem. So far so good, everybody? Oh? Now, then the issue comes here is like this. In fact, there is no closed form for Planck's radiation law over a band. There's no closed form. So I cannot obtain an analytical expression for this area. So what we normally do is that we do an approximation. Okay? So I zoom into this strip here, and this is what you're seeing. So from lambda 1 to lambda 2, I want to find what is the area under the blue curve, Planck radiation law. But I have no way of directly measuring. I'm going to do an approximation. I'm going to take the midpoint of lambda 1, lambda 2, and then from there I get a certain height, isn't it? I shall construct a rectangular area here. And this rectangular area is used to approximate the actual area under the blue curve. Is it clear? And this approximation is okay because lambda 1, lambda 2, they are pretty close. Okay? Now in fact, if this blue curve here, if this is strictly a straight line, then this is not approximation, this is exact. But in reality, this blue line here is not straight, it's a little bit